Two 10 kilonewton forces are applied to a 20 times 60 millimeter bar. Determine the stress at point A when B is equal to 0 and when B is equal to 15 millimeters and when B is equal to 25 millimeters. So in order to determine the stress, we'll use the flexure formula. Sigma is equal, but we notice two things. We notice that there is also an internal load. So the total stress is going to be P over A minus MYI, right? And the Y, this is the Z-axis. So this is about the Z-axis and the moment is about the Z-axis. So let's make a new depiction of this. Oh, because we're in black. Let's make a new depiction of this because I feel like it's important to be able to visualize it. So here we have our fixed support here. And we're going to have our x-axis here. And we have a load at 25 away. So right here, we're going to, and I'm going to change color for that. We have 10 kilonewtons at a distance of 25. Right here, 25 millimeters. And this B, this is a distance B with another force. So we have a variable position for that. And then, of course, we have our 30 millimeters here. Right. So let's think about the first scenario. For the first scenario, when B is equal to 0, we're going to have what? Well, we're going to have an internal load that is 20 divided by the area, which is 60 times 10. You can see that by inspection. And then we're going to have a minus, and we're going to have the moment. Well, what moment about the z-axis, which comes out of here, are we getting from this top one if B is at 0? Well, none, right? It's not going to rotate it about the z-axis because it passes through the z-axis, its line of action. So we're only going to have a moment that is this way from this bottom one. And so is that going to be a positive or a negative moment? Well, it's going to be, let's just say it's 10 kilonewtons times 25 millimeters. 10 kilonewtons times 25 millimeters. So we'll convert everything to meters. Let's see if that's a good idea. Because we have kilonewtons over millimeters squared. So actually, we'll keep it like that. Newtons. And this is millimeters squared. And here we're going to have our moment, which is 10 kilonewtons. So 10,000 newtons times 25 millimeters. And then we want to find the stress at A, and from the neutral axis, A is 30 millimeters. And then we want to divide by I, which in this case is just going to be 1 over 12 times 10, not 10, and I messed that up here. It's 20. Because you see, it's 10 and 10. So it's 20. And the total height, 60 to the third. So this should give us the first answer. 20000 divided by 60 times 20 minus 1,000 times 25 times 30 divided by 1 over 12. 1 over 12 times 20 times 60 to the third. Now, the only thing that you have to be careful of is if this moment is going like this, then with the right-hand rule, my moment vector is pointing this way, which means the moment is positive because in the positive z direction. Otherwise, I'd have to put negative. So that's something to keep track of. So let me see if I inputted everything correctly into the calculator. And if I did, we should get what? We should get... minus 4.16 megapascals. Minus 4.16 megapascals. Now let's do, this is for when B is equal to 0. And what about when B is 15? Well, this is where what I was talking about in terms of sign matters. So the load is going to be the same. The internal load is still going to be the same. And we won't put the units anymore because we've analyzed them. But we're going to have our 10,000 and at a distance of 25, A is still 30, but the moment is going to be the overall moment, which is going to be this one, which is positive. This one's negative because if you look at it, this one is going to go this way. Right-hand rule, the moment vector points that way, which is in the negative z direction. And so we're going to have minus 10,000 at a distance of 15. That's going to be our overall moment. A is still going to be at 30. And then this is still going to be the same. And so let's input that into the calculator. Let me copy this and paste, and then I will take 10,000 times 25 minus 10,000 times 15, put it in its own parenthesis. And the bottom is going to be the same. And so what I get is 8.3 megapascal. That's for a B equal to 15 millimeters. And then we do the same thing for the third one. The load internal is going to be the same, but what is B now? B is 25 millimeters. So minus 10,000 times 25, we notice that that's 0. So what that means is that there would be 0 stress when B is equal to 25 millimeters. And that's because the two would offset each other. So I hope this was a useful... I hope this was a useful review for you. Hold on, I'm not completely sure I did this right. B should be 25. It's not 0, sorry. My bad. This component is 0, sorry. So this would be 20000 divided by 60 times 20. So don't make the same mistake I made. And that's going to be 16.7 megapascals. Now, I am 1 unit off, I think. Let's see. 60 times 20. Oh, I think I'm correct. All right. So I hope this was useful. So one of the big items is, don't forget this term. Don't forget. For eccentric axle loading, it's easy to forget. And it was useful for me. So I'll see you next time.